And these last two talks are part of tonight's SEMPS meeting, and we can also recall that the 10th SEMPS meeting will be at King's College in about 2 weeks, on the 17th of July. So now we have Carolina Matte Gregory from the University of Oxford, who will talk about supergravity duals to high-dimensional supersymmetric theories.
Hi, it's the organizer for inviting me. This talk will be about these two papers that both of them in relation with variety of different parts. Both of them talking about supergravity and so supersymmetric gauge theories. So the first one was basically finding supergravity duals to supersymmetric gauge theories on isotropic 5-sphere background. So that means the supergravity obviously will be the bulk of this Porsche 5-sphere. And we're going to use Roman supergravity to describe this supergravity. And that is because Roman is going to be consistent truncation of type to a massive type 2A string theory. So we're going to find some supergravity solutions to that. And then, in order to compare to supersymmetric gauge theory, we're going to look at the holographic free energy that was we saw yesterday, where it comes from Leib's talk. And then we're going to look at Wilson loops as well. Then the second paper is basically most of the rest of the talk. I'm going to define SU2 structure, so the G structure that I talked about yesterday for this case, and then talk about what you can do with this SU2 structure. And then in particular, look at new solutions. And then if time allows, we'll see how it goes. I'll be classifying some solutions with zero B theory. Right. So this is where we're going to define our supersymmetric gauge theory. So as Porsche 5-sphere, so if you have a regular round 5-sphere, you'll be thinking about your SO6, S4 isometry all squashing your sphere, but it's a nice squash, so you're not changing the topology, so the wall. You'll be breaking your symmetry to SU3 plus U1. And in particular, this isometric because this metric. So this metric can be seen as a half vibration over CP2. So there you have your half cycle bundle, and this is CP2. S is my squashing parameter, so this is very similar to what we've seen in those talks. So this is my one form, in particular D of this one form, so the derivative of this one form will give me my Kler2 form on CP2. Right, so this is the setup, right? But Imamura that worked with Porsche 5-spheres, and I think it was part of the motivation for us to look at this. He showed that to be able to actually define supersymmetric gauge fields on Porsche 5-spheres, you have to turn on your A field as well. So this is the gauge field as SU2 gauge field, and it has to be on this form. So here you can think of this A3 as a 3 type of SO3. So that if you have A1 equals A2 equals 0, and just A3 equals A. And for it to actually be supersymmetric, then the parameter K has to be either 1 or minus 3. And this will lead you to 3/4 BPS and 1/4 BPS solutions. I mean, obviously, this is not how you get there to the supersymmetry. To actually get to the supersymmetric solutions, you have to solve your King's-Spinner equation. Well, in this case, an algebraic equation. So this also that we talked about, and they got like some analogous to these equations. So this is my differential equation. So this is my King's-Spinner equation. There is a differential one, and then it's supplemented by this algebraic equation. Chi plus and minus are doubled on this SU2 symmetry, and the ones are just algebra on this 5 dimensions. Right. So we have this chi minus and chi plus, they actually respect this conjugation thing. So we define the charge conjugate as chi c equals some conjugation matrix, and chi conjugate star. So this is consistent with imposing select Majorana condition. So chi minus is equal to chi plus conjugate. And we can use that to then relate the solutions that we get from those two equations that we had just before. So in the case of having my Q equals -3, I have the quarter BPS solution, which is a much nicer solution that we're going to see in the next slide. So, I mean, it's just a function of tau. Tau is one of the coordinates on the CP2, and C plus and C minus are just integration constants, and they relate each other to this embedded manual function. In the case of the 3-quarter BPS, I mean, it's a much uglier expression. In particular, I didn't even put all the expressions here. So these S's are not very nice functions of theta phi that are also coordinates in CP2. And these A's, gamma is just a function of S. And all these A's, so I have A, 1, 2, and 3, all of them plus and minus, they're all integration constants, but all of them are also related to my condition. Right, so this is my supersymmetric gauge theory on this squash device here. But I will want to, at some point, compare it to the supergravity rule that I will construct. So to do so, we can use BPS quantities, and in particular, like we talked yesterday about the partition function. So we're going to look at the free energy in this case, and for free energy, we need a partition function. So this is the perturbative partition function for squash device here, also deduced by Mamura, so the guy that said that we need to beyond. And also the guy that said that this should make it in spinor equation. This also comes, I mean, it's exactly the same theory, so it comes from this twisted production of R cross S5. And I mean, I'm not going to be entering in details here. I think just the nice thing to see is that this depends on this B, and B is this triplet, where, I mean, all of them just depend on S, but I have different ones for depending on the amount of the symmetry that I want to preserve in each case. Or not that I want, but I will preserve in each case. Right. So this perturbative partition function is actually valid for a general gauge theory in its 5 dimensions. But we, in particular, looked at the case where the gauge theory is this USP2N. And that is because these gauge theories, so this actually comes from, just to relate again to that story, this comes from some D48 brain system. So these are, in large and known to have duals in the massive type 2 supergravity. And it's good because we know some computation of this that has, and it is an exclusion of 6-dimension supergravity. So we'll be able to use that. Now the computation on the large M unit can be carried using matrix-level solid point method. This was developed by Zirkov and Kufu. They also saw that the perturbative partition function is actually enough. You don't need to look at the non-perturbative one because their contributions will be expressed on the large n unit. So after doing this computation, what you find is free energy given by this. So it's only a function of these B's that we just saw. And you can relate to the free energy in the rounds here. In particular, if you just plug in the values for this, you see that for the quarter BPS, this contribution completely vanishes. So the quarter BPS free energy is completely independent of this quotient. Right, so we want to find exactly the same thing for the supergravity. Right. Right, so in order to find this gravity duals, again, we're going to be looking at this Roman supergravity. So I just told you that it's a consistent location of my massive type 2A, and now I'm saying it's on S4. This means that you have an uplift of this back to my 10 dimensions vehicle supply ansatz that I'm going to present to you in a second. But another thing that we should think about this theory are the fields that are on it, or they could be on it. So we have dilaton that we've seen this past couple of days, a two-form potential B, a one-form potential A. We have the gauge field as a two-gauge field A1 that we looked at very similar to the one that we just had. So we can look at the dilaton actually as a scalar field defined by that X. That also looks like something Zeniac at some point. And then the field strengths are given by this H, that F, and the Fi. In particular, it can actually gauge away the first A. So I mean that we are going to leave this alone. And if we take my AI from the gauge field to be just A3, I don't have to care about the second part of that as well, so it simplifies a little bit. Anyways, so this is the ansatz for the uplift to 10 dimensions. So this is my 10-dimensional metric. So this is basically my M6 manifold times some S4. Not quite S4, it's actually just half of S4. So this parameter psi actually goes from 0 to pi over 2. So this is actually, this metric is singular at psi equals 0. But it's really everywhere else, especially in pi over 2. And in pi over 2 in particular, so this psi, for constant size, you will have, the slices would be 3 spheres that you can define. They're defined by the Euler angles. And when you have this psi to be pi over 2, these 3 spheres actually shrink to 0 size. So this isn't. And these are my fields. So these are also similar to the result there. So this is my 4-4 Ramon field. So 3-4 no Schwarz, no Schwarz, and then 2-4 Ramon, and again I have something like that. Right. Now this is back to 6 dimensions. So the supersymmetric gauge fields that we defined before, they'll have their gravity rules in Euclidean Roman supergravity. So this is Euclidean described in a Euclidean signature. So you have your equation of motions for all your fields, and also your Einstein equation given fields. Right, so if you want to find a solution to this Roman supergravity, obviously you have to find fields that solve all these equations, and you can do that. But this is just a solution to these equations in particular. To make them supersymmetric, you obviously have to also have them being consistent with your Killing spin equation and your dilating equation. So this is like something simple coefficient. We're going to go first. Anyway, so you have to solve all those equations and then make sure that they respect also these 2 equations to be some supergravity related, supersymmetric gravity. Right. To solve those equations, we're going to give an ansatz for this question. Well, for all my supergravity space. In particular, we want this to respect this symmetry, especially on the boundary, so this symmetry S3 plus U1. So what we do is, well, it's the same metric basically, or very similar metric to what we had for the supersymmetric gauge fields, but we have an extra dimension there, the dr direction. So this r direction is basically my radial direction. I want this, so this is such that I have a conformal boundary on r equals infinity. And what I'm looking at is, well, I want to find solutions to this with a topology of a ball. So I want my r to run from Some are 0, that is my origin, it's my ADS radius all the way to infinity. My fields that were beyond, so as I said, we had all those fields for Roman's theory, or all those fields here, but I can simplify those a little bit, so I'm left only with beta b equals this, and my gauge field A given by that. To that, obviously, my scalar field comes from right. So now I plug all these ansatz into my equations of motion. So that's the first step, right, to solve infinite solutions. And that gives me this horrific set of second-order couple differential equations. So this is what they look like. You have to solve this. And it looks ugly. It's ugly, and we couldn't really solve this analytically. But I mean, you can solve, we have 7 equations, 7 functions, and so forth. You can really solve anything order by order if you plug expansions on this thing. So that's what we've done. We wrote expansions for every single function, and then we solved it with the expansions. So in particular, this is the conformal boundary. So meaning these expansions are around r equals infinity. And then you solve order by order all those equations, and this is what you get. You see that there are many free coefficients around, and a few of them are going to go away because you still have to impose more things. But this is what this looks like in conformal boundary. You can also do your expansions, and particularly you need this for the energy, but you also can do these expansions around the ES. So this is basically around your ES vacuum. So this expansion is an expansion with a delta, and then I take the delta, so I have it here, and then you take delta to be small, right? Right. So this is not really a solved part of this. This is just a setup. But the first terms here are solved, and in particular, if you take delta to be equal 0, what you have is just these first terms, right? Here you have no terms. So meaning that for delta equals 0, what you have, your setup is actually EDS 6 vacuum. Your metric is the only non-trivial field, well, and x6 equals 1, but then the fields are all equal 0. That actually set out my ADS radius, that is going to be 1 over square root of 6. Notice that I don't have a beta here. You have some parameterization freedom, and we took beta to be fixed, so I don't have beta in any of those two. Yeah, in particular, beta is actually this first term on comma, exactly the same, which was probably not our best choice, but at the moment it didn't matter much. Right, so this is what we get, and then you have to impose the Latino equation and Killing spinor equation. So they have to hold so that we have a super symmetric solution. And then what you get, I would have to do 4 different slides to all the solutions. So what you get really is, again, a 3/4 BPS and a 1/4 BPS, which is what you expected because it has to agree with the gauge theory. And then the 3/4 BPS is actually a 1-parameter family only, and it only depends on the squashing. And the 1/4 BPS is a 2-parameter family, and that depends on the squashing, and also this first term of my SO2. Right, so you can get there and you can get your solutions to the supergravity. But to then be able to compare, you have to actually compute or BPS particles. So that's what we do. So here in this case, we're doing the free energy, again, the holographic free energy. And then to compute this holographic free energy, we have to be able to evaluate the renormalized on shell action. So the on shell action, again, I spoke about this a little bit yesterday. So it's defined on this manifold M6. It's the one defined by the metric, and with the boundary U6. Now this is already plugging the Romans ansatz into this. So these are the equations, the integrals that I have to solve. I also have to include this given talking term. This is such that convergation, especially on the boundary, I'll still have my action spitting out Einstein equation. So I have to solve this, but there is an issue, right? The issue is that if you just solve these integrals, they diverge. But these divergences are not too bad. So they're actually proportional to local integrals on the background boundary metric. So what you can do is you can modify this integral in such a way that you can include some terms that will cancel these divergences. To do so is well, it's just procedure, just manipulation. What you have to do is well, you said you have all those fields that are going to be plugged inside those things. You can look at the expansions. You can look at expansions for all those fields and then plug them in. In particular, looking at you have four conformal boundary on infinity, right? So you could actually look at your metric as in the Verforming Graphen form, so that you have then your conformal boundary on 0. Anyway, you get expansions, you plug your expansions on these things, and then again, order by order, you look at it. Does this term diverge? Does it not? And then you start picking up the terms. And then what you do is just then you subtract all the terms that diverge in the end. And it's alright because it's a finite number of counter terms. So these are all the counter terms that we have for this particular case, which might look bad. This highly depends. Well, it depends on the fields that you have, of course, but it highly depends on the dimension that you're working on. So in lower dimensions, you have lower counter terms to work with. So then I have all those three integrals plus this integral. I put them all together, and they spill out a finite result. So or finite result. So to integrate, actually, you do some integration. I put it on the R. So you do the integration overall, of course, but my fields only depend on R, so I don't have to care about that too much. Then I have to just avoid them. My integration on R then will be from the ADS radius, and it should be all the way to infinity, but what we've done is ADS radius all the way to a cutoff, and then we send this cutoff to infinity. And then the result is exactly the result that we get. I will only large image. That is nice, it's check this here. Another thing that you can check is the Wilson loops. The Wilson loops are also BPS quantities. And you can compute both of them. You can compute them in both sides, right? That's what it means, the loop So to compute the Wilson loops in the gravity side in particular, then you have to uplift the solutions to massive two-way supergravity, and then this Wilson loop will actually be just the action of a fundamental string sitting on the air, and that will agree with the Wilson loop in the fundamental representation in the supersymmetric theory. In large range of this. So first on the gauge theory side, so we're computing the VF of this Wilson loop, and then in this fundamental representation of the gauge group that we chose. It is computed like this, again, not many details. In particular, this is a fixed coordinate that we have to use to compute the energy on the other side. And this is a curve that is wrapped by the Wilson loop. And then once you compute this, your integral again, your result will depend only on this the quantities that we can find. So it's again the same, and they vary from 3/4 BPS to 1/4 BPS. In the gravity side, so we, again, as I said, you uplift to 10 dimensions, and you have this ABS6 across S4 kind of. Your fundamental string will be sitting on the north pole of my internal space S4. So this, as I said before, this is where I have, the nicest place. As I said, that's when the S3 slices go to 0. Right. So you compute this sort of the north pole, and you want the action of this fundamental string. So the string grabs a copy of R2 that is actually a great action and you was on the curve as one. This turns out to be hidden direction that is that E5C, I changed the prediction that one. So that special direction that I had already in my squash 5 series at the very beginning. But this, it's easier to see later on. So the fundamental string action is given by this, and then again you can analyze what happens in phase and you get exactly the same thing that we had before for this thing. So again, perfect agreement with my supersymmetric theory. Right. Now on to the second paper. Here, so we've done all the hard work in the first one for a very particular case, but what we've learned in these 2 days is that if there's something you can do is define a key structure for the background. So in this case, maybe this is not best slide to make a point on this. We know that we can construct bilinears out of 4 spinors. So this is my spinors, and obviously they respect my ground condition. So I can write, for example, these scalars, and in particular I'll be using a lot of S. Then f has to be 0 because from my differential conditions on this spinors, I'll find that either f is equal to 0 or my gauge field is equal to 0, and I need my gauge field, so f is equal to 0. And I can write, so this epsilon is epsilon plus and epsilon minus. And in particular, epsilon plus, I can write this square root of s, because theta is quite equal 1, and then the same with then theta 2 star, such that this theta 1 and theta 2 are orthogonal unit in one kind of spinor, so that they respect these conditions. And these together, they define my SU2 structure. So in 6 dimensions, this structure can be defined by this K1 and K2 forms. And they do this JI2 forms, JI1, 2, and 3. These are defined by this, but it's the size of your matrix, right? So if you put a gamma of one size, then you have a 1 form and 2 form. Right, and then with this, you can define also this J equals J3, and then big omega equals J2 plus Ij1, complex structure. So this is my canonical SU2 structure, and it's defined by this. In particular, I have these conditions on omega and J, and these are actually my volume forms on the dimensional space that I have. That is my CP2 up to this point, at least. It was my CP2. So we constructed this SU2 structure, and now we can look at what constrains this SU2 structure. So what we talked about is that you can you just create these scalars, but then you can plug in different sizes of gamma matrices and create more and more things. So that yesterday did a couple, I think, like up to 2 forms, I think. We did it up to 3 forms. I mean, you can do it forever. At some point, the differential constraints that you get from them, they start getting redundant. We probably could have done a little bit more, but we did up to 3 forms. So looking at say epsilon dagger something epsilon and epsilon transpose something in an epsilon. And these are our differentiable strings. I have 2 slides of them, just to show you what they look like. They're obviously not algebraic equations, but they are only first order, so it's very nicer in any case. There's a 9 using here. In any case, so these are all of them, and so these are the differentiable strings for all of this structure that I just showed you. And what we have shown is that if you want to find supersymmetric solutions in this form, so this thing here, this is actually K1. So I don't know why I didn't write K1. So this is K1 plus K2. K1 squared plus K2 squared plus this GDC2. So this is a 4-dimensional metric, such that your structure behaves in this way. Plus, size anyway, slider was also mentioned yesterday. There's our K vector. This is also the case here, and such that you have this. So this is obviously, I mean, we got this from differential constraints. So this is how you write your gauge field A. So if you have this setup and those differential constraints that we just looked at, then if you solve those differential constraints, there are always going to be supersymmetric solutions to this, provided that we also impose this flux equation that we didn't find from up to 3 form, bilinears that we constructed. We showed, so we know that to construct these bilinears, we have to plug in the Euclidean spinor equation into the linear equation. But we show that this, if you supplement it by this flux equation as well, they not only imply Euclidean spinor equation in the equation, they also imply all the equations of motion and Einstein equation from Brown's theory. So this is really like either you solve the way that we did first, like all those equations of motions, all those ugly second order couple differential equations, plus then afterwards solves you Euclidean spinor equation in the linear equation, or you solve these equations that are not the nicest equations, but it's just one set of equations in linear boundary. Now, of course, it's a much simpler system than the previous one, so much easier to solve, but it's not that easy to solve by itself, meaning that getting a general solution to that, it's not super easy. But I mean, we can always plug an ansatz. This, in particular, is just the ansatz for Squash 5U. And we decided to, see what it looks like. And it turns out that plugging in exactly the same ansatz in these equations, now we're able to get analytic solutions for the 3 coordinate ideas. So there's, so it's exactly the same ansatz, and there's a couple of slides just showing. So this is already fields. It depends on this Fi. So if you write Fi like this Ki FR, you see the lower fields will depend on the big Python thing, K1 squared, K2 squared, K squared. And we can also, I mean, you can move it around so that you can write all your fields in terms of these things so that they simplify a little bit. You can take a few of them away. They all look more or less like this, but there's a couple of ways that you can look at them. Furthermore, doing this implementation invariance, that of course that made us treat beta to be something fixed. We can also make all the fields depend on our just through beta. So we can define this thing, and then this is just a new variable. And then we can solve our equations for this new variable. The solution does not look nice, but they only contain roots and integrational functions, and this is going to give you some analytic solution to the 3-part BPX. We tried looking at the analytic solution for the 4-part BPX, that didn't come out so nicely, so we left it that way. Right. Another thing you can do is actually look at some generalizations of the things. So, in particular, simple generalization to make. So before we had something, some vibration, two-dimensional vibration over CP2. Now I can think of not a CP2 anymore, but some generalization of that. Euler-Einstein equation, Euler-Einstein manifold here in my four-dimensional metric. And then now I have a new answers that I can just plug into those differential equations that I got from my bilinears. Now, just looking at these ansatz and looking at the conditions that we've got for those bilinears, what we get is really like just in the identifications. So this is from the K1 part of it. So K1 already gives us what gamma looks like, and then K2, and then we can look at omega and J. This equation also came out at some point, also saying that come from differential constraints, but this is happens here as well. And my fields all they will look like this. Now, if I get these things and plug into those differential constraints that I had before, then they simplify to this. This is like in one slide. So they are first order differential equations, they're coupled, but they don't look that bad, and you can solve them not analytically, unfortunately, or not that you manage to. But again, you can always solve something order by order. And that's what we do here. You solve it again, R around infinity, R around your ADS radius, and solve the two, and then you can again start looking at the GS quantities and then compare it to the gauge side. So the holoelectric free energy, again, very close. I mean, you can just take the same expression. Those counter terms that worked on that case, they are exactly the same. We're still working on Roman supergravity. So you don't have to do all that mess again. You can just plug those in. And this is the type of free energy that we look. And again, you can compute on the large n limit. In the field theory, you can do a very similar computation as well, and the result will be perfect. I mean, notice that we only have one now. This is actually it's a very similar result to our portable PS from the previous case, and that's the only one that we have. You can again look at Wilson loops, and both again in the gauge theory side and in the gravity side, do the computations, and they again are going to be. Right. So another thing that I've been looking at, so as I said, so that SU2 structure and its differential constraints, they're nice, they're not so easy to solve by themselves, but you can always just plug some extra, make some extra assumptions, right? So I just presented to you a couple of concepts that you can plug in to simplify. Another simplification that you can do is really just try to get rid of some maybe unnecessary fields. So I decided to look at what happens when I take B to be equal to 0. So we know that A has to be turned on, but what happens to B? So in particular, so I didn't put many details here, but in particular you can show that if you take B equals 0, so those equations will really simplify. And then you can show that whatever solution that you get from these equations will always give you a metric on this particular form. So now I think I just should have when I change the notation, but now this row is kind of my gradient direction. And again, so this is basically K1, and this K2, and then this is my four-dimensional metric where there's vibrations. So this G is a one-parameter family of Taylor metrics, depending only on rho. And also from this differential constraints, I can get this relation. So this is a constant. And also, sorry, maybe to look at it, but this relates then this rho that is in my radial direction, and this is from this structure and my X field. And then you can get further differential constraints for this case, and in particular you can look at this evolution equations for this structure, for SO2 structure. So you have this derivative in this rho direction, so this is really indicate two direction. And then this is how it behaves. Yeah, notice that this is also in the same. Oh my god, this is already here. Right. We also get Einstein-like equation. So my Ricci form is given by this thing, and some extra constraints on the rest of my structure. So this is what my system of differential equations coming from the bilinears became. So these 2 pages now, this is the setup. This is all they have to respect to give you a solution for a Roman supergravity with the B field equals 0. Now, we can look further what this means. And in particular, we can look at this Ricci form. So in order to have a 6-dimensional complex manifold before making a metric, then we actually need some constraint on a 3 form, no longer a 3 form. But this implies that this sigma has its derivative. So I mean, when you take the external derivative, you obviously have to take in account all the directions, right? So in particular, this won't have any contribution on the K1 direction or K2 direction, so it won't have contributions on the extra 4 directions that we have. And I mean, it will never have contribution actually in the K1 direction. We knew that already. I knew that I didn't include this, but that was the thing that we knew. But this just implies that it has no derivatives on the rho direction, on the radial direction. But that implies that all these things, so S and theta follows the SO2 structure and X, my field X, they have no dependence on those extra directions. So they don't depend on the phi direction, but the psi direction will just tell you. So that's the K1 direction. So they can only depend on, this is what it says. Now we can compute this default of the Ricci form, this is called the Ricci form, and we find that it's equal to 0. And what it means is that this Ricci tensor has 2 pairs of consonant values, and if these eigenvalues are the same, then my 4-dimensional manifold on my ansatz, it will be a Taylor-Einstein manifold. Otherwise, if they are distinct, then Goldenberg conjecture implies that this N4 will be locally a product of 2 Riemann surfaces with distinct constant curvatures. So then I can actually look at those solutions. I mean, I can look separately at the K-Einstein and at the product of 2 Riemann surfaces. In particular, so starting with the K-Einstein case. So for the Einstein metric, I have this Ricci form to be proportional to my J hat. So this, I started putting hats because when I came from my differential constraints to this, I had to do the next effect. Like I could factor out that x minus 2, so I have a J hat. So it's basically what it means. There's a factor of 2 squared or x squared somewhere. But that's it. So what I mean is that my Ricci form is proportional to my J that comes from my SO2 structure. And constant of proportionality will depend on your own rows, so this is a regular action. And then also what you also get is that this D4 sigma is also proportional to J hat. Now, it's proportional, so I mean I can just call it a J middle thing, so that I can omit any constants or something. And then I have the same for this J hat with relation to J twiddle. Now this will enter the form of the metric here. So you can write your Ricci form as this with OK. and then you can plug this into my equations that I got here, these equations, and then look at what things look like. In particular, so I get very particular types of solutions, and you get like this particular form for f of rho and the cos and x, and your metric in this case will always look like this. This amazing. I did some extra mistake here. Now you see that you have an R, but R is R and rho are related by a constant. So this is what it looks like. Now, going into the product of two Riemann surfaces. Now I have to take into account, I should have probably written the metric of the general answers. So I can still consider that the metric, that the Ricci tensor is proportional to this j hat. But now j hat is actually in position of some j1 in one of my Riemann surfaces and j2 in the other of my Riemann surfaces. And then I have two functions multiplying them, depending on rho. And then also for for sigma, I have again this type of composition with some constants. These are real constants, not anyone. Now, so we have these two forms, G1 and G2, such that they do not depend on the direction. And then I can release all this movement on the metric so that I can write them in terms of my metric, in terms of these j's, and then I have this k1 and k2 that are also constants. Right. Now, if you plug all those things again in those general equations that you got for p equals 0, so those differentiations that we got, what you have for x and for cos theta are those things very particular. But for f1 and f2, what you get is f1 is very, very similar to what you get when we kill Einstein case, which is not surprising because, well, then when you have f2 to be actually some proportionality and f1, and these are actually the terms, the constants that I have sitting in front of my j1 and j2, they end up canceling each other. And then in the metric, what you have is that those two Riemann surfaces, they actually cannot be different. And so they have the same curvature and they go back to my Taylor Einstein. So what we find is that if we take Roman supergravity with B here being equal to 0, and then when you ask this 6-dimensional manifold to be complex, so that's when we got this before theta equals 0, then Taylor Einstein solutions as a basis, my 4-dimensional base is the only possible solution I can get. Right, and we had a very good time, so discussion and conclusions. So just summarizing our results. So we got our free energy in this form that is just a function of these V's. And then by looking at it, so again, what we've done when we deformed it, we decided, I mean, the formations will be just to a point that you wouldn't change the topology of the sphere. So you have a steam topology of your 5 sphere. And then maybe you could do some other types of squashing, but as long as you do not, as long as you still have the topology of the sphere, we conjecture that this should be the free energy for it, always. And then for the Wilson loop, I mean, again, it only depends on these B's. We thought that, well, it's natural to make exactly the same conjecture. In fact, I didn't put the results here, maybe I should have, because I had the case 5 minutes ago. In fact, using this SO2 structure, one of the applications, I mean, you actually have many more applications, but one of the things that we've done in the second paper was to use this SO2 structure to rewrite the action of the fundamentals. So what happens is, I didn't say much about that. That was actually much easier to compute than the free energy. It turns out that it is an integral of a total derivative, so it's obviously much easier. But using this SE2 structure, it gives it to you, like here, this is the total derivative that you have to solve, so it makes it much easier. And then, by showing that, we actually proved that for this case, for Lewis, yes, I mean, this is true. This will hold for whatever solution you have as long as the topology is still topology applies. What we think is that we think this is probably, I mean, you'll probably be able to do this for the free energy as well, meaning like using the SE2 structure to be able to rewrite the integral of this action. But we didn't manage to do that. The conjecture stands, and it would be nice to prove it. Right. Also, I mean, we showed that this SE2 structure is actually very useful to find new solutions. So we found a few, but again, we only found one analytic solution. So it would be nice to see if we can find more analytic solutions. And but also another nice thing that one could do is look at solutions with different topology, like using this thing. This is something that I've been doing in my master's. So yeah, that's, so this is, I didn't unfortunately put any references in the middle of the presentation, but all the references for everything is said, I think, for most of them. I'm not sure if this last part here had references on these papers. This is actually from, mostly, it's very closely following the paper that Dario has with James Parts, from I think 2004, on how to classify this type of solutions. And the rest, I mean, we will be in.
Questions?
Quick one. Can you say just a little bit more about what you are going to publish?
Right, so as I was saying, on the part of trying to find solutions, another natural generalization, so we came from SEMPS to generalizing. So the next step would be now considering this product of two union circles. So that's what I've been looking at, and this is where the definition is still one. So that is a much more complicated set of equations, because then my differential constraints, they actually split, right? So I have many more equations to solve. But it seems like I got solutions now. So I have solutions for these two, and actually, like not as the frustrating case would be closer. So now it remains to actually compute the case quantities. I mean, it should probably call constants.
And the way if there were any results?
Yeah, I don't know actually. I haven't looked into that because for these two cases, the Einstein and the squash type theory, it was quite, it was basically done. But yeah, I don't know if it is done.
I'm not aware of it.
Yeah. So yeah, I'll have to look at it here. See. Anything else? Yep.
I'm just wondering what the status on the Goldberg conjecture was.
The what?
The Goldberg conjecture, they used the conjecture.
Yeah, you want to know the statement.
The status is it proved?
Not that I've heard of, no. Maybe, yeah, I mean, it's not a conjecture, right? Not that they are. Sorry. Yeah.
Any ideas on how to maybe get some analytical solutions in some setup, or is it,
I mean, my intuition is not that great, if I'm honest.
okay.
But yeah, no, I think you look at it and you think, oh, maybe if I do this, if I add this special function here, if I,
Right.
I have no idea
Okay.
in mind how to do it at the moment.
Okay. Any more questions? No? Let's thank you.